Hello everyone, my name is Vandana. I am from BSc Chemistry Honors, second year. Today my inorganic chemistry topic is chemistry of lanthanide elements. We have learned that the elements in which the last electron enters the f orbital of their atoms are called f-block elements. In these elements, the last electron is added to the third to the outermost, called anti-penultimate energy level. It means F minus 2f. These electrons are called in-transition elements because these constitute transition series within transition series d-block elements. They consist of two series of elements placed at the bottom of the periodic table. These two series are formed by filling the electrons in 4f and 5f orbitals and are called lanthanides and actinides respectively. The series involving the filling of 4f orbital following lanthanum Le Z is equal to 57 is called lanthanide series. The elements present in the series are called lanthanides. There are 14 elements in this series, starting with serum Z is equal to 58 and ending with lutetium Lu Z is equal to 71. The name lanthanide is derived from lanthanum, the first member of the series. These lanthanides are also sometimes referred to as lanthanums. All the elements have closely similar properties and therefore are considered together. The reason for their similar properties is that 4f orbital in which the electrons are added are embedded in the inner shells, while 5d and 6s electrons which have similar configuration are exposed more to the surroundings. Because of their similar physical properties, their separation and identification proved to be very difficult task. The first stage in their separation was to get them as oxides. Therefore, the occurrence of the oxides of the lanthanides was very rare. Therefore, these elements have also been called rare earth elements. Nowadays, the term rare earth is not used. Their substance deposits occur in Scandinavia, USA, USSR, and India. General characteristics. The important general characteristics of lanthanides are discussed below. Electronic structure and position in the periodic table. The lanthanides involve the gradual filling of 4f electrons. It may be noted that the energies of d orbitals 5d and the next inner shell or f orbital 4f are closely similar to, and therefore the order of filling the 4f orbital in the atoms show quite irregularity. At lanthanum Z is equal to 57, both 5d and 4f orbital become stable due to increased effective nuclear charge as a result of the poor shielding effect of 6s electrons. Therefore, it is observed that at lanthanum the incoming electron enters the 5d orbital and its electronic configuration is Xz5d1 6s2. However, as we move further after Le, the energy of 4f subshell becomes lower than the 5d subshell, and therefore the next electron in the serum enters the 4f subshell. The electronic configuration of serum is Xc4f2 5d0 6s2. The filling of 4f orbitals continues till we reach the ytterbium, in which the 4f subshell gets completely filled. Now, after 6s and 4f subshells have been filled, the next electron goes to 5d subshell. The configuration of lutetium is xenon 4f14 5d1 6s2. This constitute lanthanides. The general configuration of the lanthanides may be written as xenon 4f 0 to 14, 5d0 to 1, 6s2. Electronic configurations of lanthanides are given in the table. 1. From element lanthanum serum to lutetium, having symbol atomic number 57 to 71 and outer electronic configuration. Now physical properties. The important physical constant of lanthanides are given in the table 2. Ionization energies. The lanthanides have fairly low ionization energies. In general, the first and second ionization energies of the lanthanides increase with increase in atomic number, but the variation is small and irregular. The variation of ionization energies with atomic number is shown in the figure. Here, the ionization energy is in kilojoule per mole, and along the x-axis the atomic number is from 56 to 72, and the atoms are lanthanum to lutetium. The first ionization energy series and the second ionization and further third ionization energy. Now, important physical constant of lanthanides table. It is clear from the figure that some derivatives are observed in the regular increasing order, such as for EU, GD, YB, LU. These are attributed to the stability of half-filled and completely filled F subshell. The first ionization energies are of order 560 kJ per mole, and the second ionization energies are of order 1150 kJ per mole. These values are quite comparable to alkaline earth metals, especially calcium. First ionization energy 589 kJ per mole, and second ionization enthalpy 1145 kJ per mole. Second point, melting and boiling point. Lanthanides have fairly high melting and boiling points. However, the melting and boiling points do not show any regular trend as we move from lanthanum to lutetium in the series. Inspection of the table 4.2 shows that europium and ytterbium have unexpectedly low melting and boiling points. These atoms form EU2 positive and YB2 positive ions and result in weaker metallic bonding because there are less than 3 electrons per atom in the metallic bonds. The other lanthanide atom gives 3 electrons per atom in the metallic bonds. Therefore, melting and boiling point of EU and YB are low as compared to the values for their lanthanide elements. Third, density. Densities of lanthanides are low, which range between 6.5 to 9.474 gram per centimeter cube. However, there is no definite trend in the density value of lanthanides with increase in atomic number. EU and YB have unexpected low values for the heat of fusion and heat of vaporization. The heat of fusion and heat of vaporization also do not show definite trends with increase in atomic number. Fifth, electronegativity series. Electronegativity values. The electronegativity values for lanthanides between 1 to 1.15 are quite close to those of alkali and alkaline earth metals as block elements. Therefore, lanthanides are expected to form ionic compounds. Sixth, electropositive character. Because of low ionization energy and electronegativity values, the lanthanides are electropositive like S block elements. Third, the oxidation states. The common oxidation states of all lanthanides is +3. In addition, some lanthanides show +2 and +4 oxidation state also. These are shown by those elements which by doing so attain the stable F0, F7, F14 configuration. For example, Ce and Tb exhibit +4 oxidation state. Serum and terbium attain F0 and F7 configuration respectively when they get +4 oxidation state as shown below. Ce4 positive Z is equal to 58. Xenon F4F0. Tb4 positive Z is equal to 65. Xenon 4F7. Second, EU and YB exhibit +2 oxidation state. Europium and ytterbium get F7 and F14 configuration in +2 oxidation state as shown below. EU2 positive Z is equal to 63. Xenon 4F7. YB2 positive Z is equal to 70. Xenon 4F14. LAGD and LU exhibit only +3 oxidation states. These elements show +3 oxidation states only because by losing 3 electrons they acquire stable configuration of empty, half-filled and completely filled 4F subshell. La3 positive Z is equal to 57 have xenon 4F0 5D0 6S0 or xenon empty 4F subshell. Zd3 positive Z is equal to 64 have xenon 4F7 half filled 4F subshell. Lu3 positive Z is equal to 71 have xenon 4F14 completely filled 4F subshell. Exceptional examples. Some other elements show +2 and +4 oxidation states even though they have electronic configuration other than F0, F7 or F14. For example, Sm and Tm show +2 oxidation states having F6 and F13 electrons respectively, in which they have one electron less than half filled or completely filled configuration. Similarly, Pr, Nd and Dy show +4 oxidation states having F1, F2 and F8 electronic configurations. The stability of these unusual oxidation states may be dependent upon some other thermodynamic and kinetic factors which are of significant importance, but these are less stable than +3 oxidation state, which is characteristic of this family. The outer electronic configuration of lanthanides in different oxidation state are given in the table, having elements La to Lu, atomic number 57 to 71 oxidation state, and M2 positive, M3 positive, M4 positive. Fourth, color and spectral properties. The lanthanides are silvery white, but many lanthanide ions have colored both in the solid state and in the aqueous solution. The color remains same even on the change of anions. Therefore, the color of characteristic of lanthanide ion. The color of the ion depends upon the number of unpaired electrons because it has been observed that ions containing NF electrons have almost similar color to those with 14 minus NF electrons. The different ions having NF and 14 minus NF and their colors are given in the table, having ion electrons and number of 4F from La3 positive to Gd3 positive and Lu3 positive to Tb3 positive, having different color. However, it has been observed that some Di and tetrapositive ions having same number of electrons, isoelectronic ions, are as tripositive ions do not have same color. For example, Sm2 positive and Eu3 positive have same number of unpaired electrons, but they have different colors. However, it has been observed that some di and tetrapositive ions having same number of electrons, isoelectronic ions, as tripositive ions do not have same color. For example, Sm2 positive and Eu3 positive have same number of unpaired electrons, but they have different colors. Some other examples are given in the table 5. The color of lanthanide ions arise due to absorption of light from the visible region of the spectrum, resulting in the electronic transition within the 4f level. FF transition. A remarkable characteristic of the spectra of tripositive lanthanide ions is that the absorption bands are extremely sharp line like bands in ultraviolet, visible or near infrared regions. Many of these bands are line-like and become even narrower as temperature is lowered. This behavior is in contrast to absorption bands of DD transition, which have broad absorption bands. The bands of lanthanide ions are so sharp that they are useful for characterizing the lanthanide ions. The main reason for very sharp absorption band is that the 4f orbital lie deep in the atom of these elements. Therefore, they are effectively shielded from the surrounding by overlying 4f and 5f's and 5p orbitals, and consequently the absorption bands arise mainly from the electronic transition within the 4f levels. Thus, the absorption bands show little dependence on the nature of the ligand. In addition to FF transition, sometimes color of the lanthanide ions is also attributed to 5D transition. The FF absorption transition of lanthanide ions have low intensity because they are not allowed, whereas FD transition are allowed. In contrast to FF transition, the FD transitions are allowed and hence show very intense absorption bands. For example, the FD transition observed for CE3 positive and TB3 positive are very intense. 5. Magnetic properties. All the lanthanide ions with the exception of La3 positive, Lu3 positive, Ce4 positive and 5b2 positive ions are paramagnetic because they contain unpaired electron in their 4f subshell. The ions La3 positive, Lu2 positive, Ce4 positive and 5b2 positive, which have 4f0 and 4f14 electronic configuration, are diamagnetic because they have no unpaired electrons. The magnetic property of the lanthanide are different from those of transition element. As we know, the magnetic moment arises from two types of motion of electron. The spin motion of the electron around its own axis produce magnetic moment called spin magnetic moment, while the orbital motion of the electron around the nucleus produce magnetic moment called orbital magnetic moment. The observed magnetic moment of the substance is due to the contribution of both the spin moment and the orbital moment. In the case of transition element, d block element, the magnetic moment mainly correspond to the spin-only magnetic moment. This is due to the fact that the d orbital are not well shielded from the environment and take part in the bond formation with the ligand, atom, ions and the molecules. As a result, the d orbital of the metal interact strongly with the ligand surrounding the metal ion. Due to the electronic field of the ligand, the orbital motion of the electron get restricted and thereby the orbital moment of these electrons get quenched. The magnetic moment of d block elements thus arises mainly from the contribution of spin motion of the electron only. The spin only magnetic moment is given by mu spin only is equal to under root n plus n2 into n, where n is the number of unpaired electrons. This relationship gives at almost correct values of the magnetic moment for d block elements. However, the above relationship is not valid in the case of f block elements. In these elements, the 4f orbital are well shielded from the surrounding by the overlying 5s and 5p subshells. As a result, the electric field of the ligand surrounding the metal ion does not restrict Iron does not restrict the orbital motion of the electron, thus orbital contribution is not quenched. Therefore, the magnetic moment of the lanthanide ion is due to both electron spin and orbital motion of the electron. This may be calculated from the relation mu is equal to under root 4s into s plus 1 plus L plus 1, where S is the resultant spin quantum number and L is the resultant orbital momentum quantum number. The theoretically and experimentally observed magnetic moment values are given in the table 6. The magnetic moments of the lanthanide depend upon the atomic number and are the number of the unpaired electron. For the ions, lanthanum 3 positive, F naught, gadolinium 3 positive F7 and lutetium 3 positive F14. The magnetic moments correspond to the spin only values. For these configurations, there is no orbital angular momentum. It means L is equal to 0. The above expression becomes mu is equal to under root 4s s plus 1, and the magnetic moment may be calculated only on the basis of the spin only value. Here s is equal to ns, where n is the number of the unpaired electrons and s is the spin quantum number 1 by 2. For F 4f0 lanthanum 3 positive and 4f14 lutetium 3 positive configuration, there is no unpaired electron and n is 0 and their magnetic moment is also 0, diamagnetic. For 4f7 configuration gadolinium 3 positive, the magnetic moment can be calculated on the basis of the spin only value. Because orbital angular momentum is 0, as gadolinium 3 positive have xenon 4f7, no unpaired electrons, n is equal to 7 and s is equal to 1 by 2, s is equal to 7 into 1 by 2 is equal to 7 by 2, mu is equal to under root 4s s plus 1 is equal to 7.9 Bohr magneton. This can be calculated as mu is equal to under root n into n plus 2 is equal to 7.9 Bohr magneton. The magnetic moment of the tripositive lanthanide are plotted in the figure 2. Lanthanum 3 positive and lutetium 3 positive are diamagnetic, no unpaired electrons. It is observed that the value increases up to niobium and then decreases to 1.47 for samarium 3 positive ion. It increases again and reaching a maximum value for the dysprosium and holmium. Therefore, it starts decreasing and become 0 for lutetium, which is diamagnetic. The unusual shape of the curve arises because when the F subshell is less than the half full, the spin and the orbital magnetic moments work in the opposite, but when the F subshell is more than half full, they work together. Sixth, ionic radii, lanthanide contraction. We know that as we move down the group, atomic size, covalent or ionic radii normally increase. This is mainly due to the additional shells or electrons between the successive periods. However, as we move across a period from left to right, atomic size decreases. This is attributed to the increasing effective nuclear charge, as a result of which the outermost shell of the electron is attracted more and more. Consequently, the size decreases. For example, the covalent radii of alkali metal increase from Li into iodine. If we consider the ionic radii of lanthanides, we get very interesting observation. For comparison sake, we can take the ionic radii of the trivalent ions, M3 positive, which is most stable. These are shown in the figure 3. It is clear that ionic radii decrease from one element to another in the lanthanide series, but decrease is very small. It has been observed that from serum 3 positive to lutetium 3 positive, the ionic radii decrease from 1.03 angstrom to 0.86 angstrom. Obviously, for an increase of atomic number 14, the decrease in ionic radii is only 0.17 angstrom. This is very small decrease in comparison to the elements of the other groups and periods. Similarly, on moving from serum to lutetium, the atomic radii also decrease from 1.65 angstrom to 1.56 angstrom, and the decrease is only 0.09 angstrom. This small steady decrease in ionic or atomic radii of lanthanide element with increase in the atomic number is called lanthanide contraction. Cause of lanthanide contraction. In the lanthanide series, the 4f electrons are being added one at each step as we move from one element to another. The shielding of one f electron by the other from nuclear attraction is quite weak due to the shapes of the f orbital. The nuclear charge, however, increased by 1 at each step. However, hence, with the increase in atomic number and nuclear charge, the effective nuclear charge experienced by each 4f electron increase. Hence, the inward pull experienced by the 4f electron increases, and thus this causes a reduction in the size of the atom or the ion. The sum of the successive reductions give the total lanthanide contraction. Consequences of lanthanide contraction. Lanthanide contraction has very significant effect on the relative property of the elements which precede and which follow the lanthanide in the periodic table. Some important consequences of the lanthanide contraction are given below. First, steady decrease in the size. This is regular decrease in the ionic radii of the lanthanides. Second, electronegativity. There is a slight regular increase. Third, electrode potential values. There is small but smooth increase in the standard electrode potential values. E naught for the process M3 positive plus 3 electron gives M. For lanthanum, minus 2.52 volt to minus 2.25 volt for lutetium. Resemblance of second and third transition series. The lanthanide contraction affects the chemistry of second and third transition series, as we can see that from table 8. There is regular increase in the size from scandium to ytterbium to lanthanum. Similarly, we expect normal increase in the size in other groups as titanium, zirconium, hafnium, vanadium, neodymium, Ta. However, the after lanthanides, the increase in the radii from second to third transition series almost vanishes. The pair of electron zirconium, hafnium, neodymium, Ta, MOW, etc. possess almost the same size. The property of these elements are also very similar. As a result of the lanthanide contraction, the element of second and third transition series resemble each other much more than the elements of the first and second transition series. Similarity among lanthanides. Because of very small change in the size of the lanthanide and in the lanthanides, their chemical properties are similar. Therefore, their separation becomes very difficult. Recently, methods based on the repeated fractional crystallization or ion exchange techniques, which take the advantage of slight difference in their properties like solubility, complex ion formation, hydration, etc., arising from very slight size difference of their trivalent ions have been used. Basicity differences. Due to the lanthanide contraction, the size of the lanthanide ions decrease regularly with increase in the atomic number. As a result of decrease in size, their covalent character between Ln3 positive ions and OH negative ions increase, and therefore the basic strength of hydroxides decrease with increase in the atomic number. Thus, LaOH3 is the most basic, while lanthanum hydroxide is most basic, while lutetium hydroxide is the least basic. The basicity difference in lanthanides are reflected in increasing tendency to get hydrolyzed due to decrease in basic character. There is a slight increase in degree of hydrolysis in the solution from lanthanum 3 positive to lutetium 3 positive. Example: lanthanum 3 positive ions are less readily hydrolyzed than lutetium 3 positive ion. Thermal decomposition of oxy salts. More basic oxysalt decompose less readily. Example: lanthanum N nitrate decompose with difficulty and is stable, whereas lutetium nitrate is unstable and decomposes readily. Solubility of salts. Lanthanide hydroxides precipitate at regularly decreasing pH values from lanthanum ion to lutetium at 7.83, gadolinium hydroxide at 6.83, and lutetium at 6.30 from nitrate solutions at 20 degrees Celsius. Seventh, size of ytterbium, hafnium, and dysprosium. Due to lanthanide contraction, the radii of ytterbium ion is comparable to heavier lanthanides, terbium, dysprosium, hafnium, and erbium. Therefore, they occur together in natural minerals. Reactivity of lanthanides. All the lanthanides are highly electropositive metals and have almost similar chemical reactivity. This is due to the fact that the lanthanides differ only in the number of 4f electrons. Since these electrons are very effectively shielded from interaction with other elements by overlying 5s, 5p, and 6s electrons, they show very little difference in their chemical reactivity. Because of their chemical similarity, their separation from another is very difficult. The lanthanides are in general more reactive than d block elements. Some of their chemical characteristics are: first, they tarnish readily on exposure to air. In finely divided state, all burn in air to form oxide, cis oxide of the formula Ln2O3, where Ln stands for lanthanide, except serum, which gives CO2. Ytterbium, however, resists the action of air even at 1000 degrees Celsius due to formation of a protective coating of its oxide. Second, all react with water slowly in cold but rapidly on heating, liberating hydrogen and forming LNOH3. Third, all these combine with the hydrogen at 200 to 300 degrees Celsius, giving LNH3. Fourth, they also combine with halogen, oxygen, and sulfur. Fifth, they act as strong reducing agents for oxides of other metals. Serum is used as scavenger of oxygen and sulfur in many metals. They react with nitrogen to form nitrides of the formula LNN. Solubility of compounds. The fluorides, oxide, hydroxide, carbonate, phosphate, chromates, and oxalates of the lanthanides are largely insoluble in water. On the other hand, the halides other than fluoride, nitrate, acetate, perchlorates, and salts of the oxoacids of lanthanides are soluble in water. The solubility behavior of the salts of lanthanides follows the pattern of the solubility of salts of group second element. However, lanthanide sulfates, unlike the sulfates of group second elements, are soluble in water. Tendency to form complex. Although the lanthanide ions have a high charge, yet they have large size of their ions compared with the transition metal. As a result, they have low charge density and therefore they have very less tendency to form complex. Their complex with the unidendate ligand are very few and form complex only with the fluoride and oxygen donor ligand. However, they form complex with a few chelating ligands such as beta diketones, oximes, and ethylene diamine tetraacetate acid (EDTA), alpha dash dipyridyl, and hydroxycarboxylic acids such as citric acid. These complexes usually have high and variable coordination number, and water or solvent molecules are often attached to the central metal line. Beta diketone complex of europium ion and promethium ion dissolved in organic solvent are used as lanthanide shift reagents in NMR spectroscopy. In contrast to transition element, the coordination number 6 is not very common. Coordination number below 6 is also uncommon and occurs only with the bulky ligands such as 2,6-dimethylphenyl and NSIME3 ligands. However, coordination number 7, 8, 9 are common, and these give a variety of stereochemistries. For example, the coordination number for lanthanum or hydroxide 3 positive in aqueous solution are thought to be 9 for early lanthanides and 8 for the later smaller member of the series. However, these ions are highly liable. The smaller ytterbium ion forms a 7 coordinated complex, and the larger lanthanide 3 positive is 8 coordinated in the complex, where ACAC is the acetyl acetonate. The structure of these complexes are a caped trigonal prism and a square antiprism as shown in the figures 4. Coordination numbers 10 and 12 occur with the large lighter lanthanides and small chelating ligands such as nitrate and sulfate. Serum 4 positive is smaller and highly charged and forms complex in the non-aqueous solvent N2O4. This is 12 coordinated serum in which each nitrate ion uses 2 oxygen atoms to coordinate to the metal. When 2 trans nitrates of these complexes are replaced by phenyl phosphate, it gives the 10 coordinated orange colored neutral complex as shown in the figure 6. The sulfates and the iodates are also known. Large number of salts of organic acids such as oxalic, citric and tartaric have been studied mainly for the separation method. These anions have chelating or ligands forming complex with the lanthanum 3 unidendate donors such as pyridine N oxide and triphenyl phosphine oxide also form many complex with lanthanides in 3 positive oxidation state complex with ligands such as En diene. It can also be prepared in polar organic solvent. For example, coordination number of 8, 9, 10 as are typical examples. As with the other transition elements, lanthanides can be induced to form complex with expansionally low coordination number by use of the bulky ligands such as NSIMe3 2 negative. This is an example of coordination number 3, which is the lowest found for lanthanides. They are volatile, air sensitive and easily hydrolyzed. They are planar in the solution but pyramidal in the solid state. With pH 3PO, the 4 coordinated distorted hydral adducts are formed. Lanthanide also form 2 main types of organometallic compounds, predominantly ionic cyclopentadienes and sigma bonded alkyls and aryls. These type of compounds are usually thermal stable but unstable with respect to water and air. The series LNC5H53 and LNC5H52Cl are salts containing C5H5 and readily prepared by reaction of anhydrous in appropriate molar ratio in THF. In polar solvent, these complexes are solvated and are monomeric, but in non-polar solvent, these tries compounds are insoluble while BIS compounds dimerize. The lanthanide also form alkyl or aryl by meta